So in this class we will study about voltage divider bias circuit. Okay. So first of all we will see the circuit diagram of voltage divider bias circuit. So this circuit, it consists of resistor R1, R2, RC, RE. Okay, and this is NPN transistor. Okay, it is now connected to ground. The direction of current IE is like this. It is base current IB, and the direction of IC is like this. Okay. So this is the circuit diagram of voltage divider bias circuit. Okay. So this circuit, for this circuit we have to determine the operating point. Okay. So we have to determine IC and VCE. Okay. So in order to determine IC, first of all we will determine IB. Okay. So if we are determining the value of IB, then we can determine IC. Okay. And also we will determine VCE. Okay. So how to determine these values? So this circuit, it can be analyzed by using Thevenin's theorem. Okay. So if we will apply Thevenin's theorem to this circuit, then it will look like this. This is Thevenin's voltage. This is Thevenin's resistance. This is emitter resistor. And this is VCC. So this circuit, it can be analyzed by using Thevenin's theorem. Okay. So if we are applying Thevenin's theorem to this circuit, then this circuit will look like this. So here VTH is Thevenin's voltage, RTH is Thevenin's resistance, RE and RC, this is RC and this is RE. Okay. So how to determine VTH and RTH? VTH and RTH. So first of all we will determine RTH. RTH, it is equal to R1 in parallel with R2. R1 in parallel with R2. This is R1 and this is R2. So if we are seeing this circuit across this resistor R2, then R1 and R2, it will be in parallel. Okay. So in this way we can determine the Thevenin's resistance. Okay. So resistance across R2, it is R2 in parallel with R1. Okay. So it is equal to R1 multiplied with R2 divided by R1 plus R2. Okay. Then we have calculated this RTH. Then we have to calculate VTH. Okay. So how we can calculate VTH? So VTH is the voltage across this R2. Okay. Voltage across this R2. So voltage VTH is voltage across R2. So it is equal to R2 divided by R1 plus R2 multiplied with this voltage. This is VCC voltage. Okay. So it is equal to R2 VCC divided by R1 plus R2. Okay. So VTH we have calculated. So VTH is equal to how much? VTH, it is equal to VTH it is equal to R2 VCC divided by R1 plus R2, and RTH, it is equal to R1 in parallel with R2. Okay, so how to determine IB? We have to determine IB. Okay, so how we can determine IB? Let us see. We can determine IB like this. So in this loop, if we are applying Kirchhoff's voltage law, then we can write VTH, it is equal to IB multiplied with RTH plus VBE. This is base terminal and this is emitter terminal. Okay, plus VBE. VBE is what? VBE is voltage across base and emitter terminal. This is VBE. Okay, plus IE multiplied with RE. This is the current IE multiplied with RE. So it is equal to IB RTH plus VBE plus IE. We can write it is equal to IB plus IC into RE. Okay, so again it is equal to IB RTH plus VBE plus IB, we can write like this. Then IC, it is equal to beta times IB multiplied with RE. Okay, since IC it is equal to beta IB and IE it is equal to IB plus IC. Okay, so it is equal to IB RTH plus 1 plus beta into RE plus VBE. We can write like this. This is VTH. So from this, how we can write the expression of IB? We can see. So from this, we can write the expression for IB. It is equal to VTH minus VBE divided by RTH plus 1 plus beta multiplied with RE. So this is the expression of IB, that is the base current. Okay, so in this way we can determine the value of IB. So how we can determine IC? Now IC, it is equal to beta times IB. Okay, so in this way we can determine IC also. Okay, now we have to apply again Kirchhoff's voltage law in this outside loop. Okay, so it will be, so we can write down the expression after applying Kirchhoff's voltage law in the outside loop. Okay, it is equal to VCC, it is equal to ICRC plus this terminal is collector terminal, this terminal is emitter terminal, plus VCE plus IERE it is equal to IC/RC plus VCE plus, we know that IE is approximately equal to IC. So we can also write like this, IC/RE. Since IE is approximately equal to IC, that is why we can write here IC. So it is equal to IC/RC plus RE plus VCE. So from this we can write the expression for VCE. So we can write the expression for VCE. It is equal to VCC minus IC RC plus RE. Okay. So we have calculated the operating points. Operating points are IC and VCE. So in this way we can calculate, we can write down the expression for the operating point in case of voltage divider bias circuit. Okay. So then how we can represent this in load line analysis? How we can do the load line analysis for this voltage divider bias? Okay, so it is VCE and here it is IC. So this graph is load line analysis. Load line analysis. Okay. Now, so this equation is suppose A. So from equation A we can write VCE, it is equal to VCC minus IC into RC plus RE. Now in this axis, in this VCE axis, what is 0? IC is 0. So if IC is equal to 0, then VCE, it is equal to VCC. So suppose this point is VCC point, this is VCC. Okay. Now if VCE is equal to 0, if VCE it is equal to 0, then we can write IC, it is equal to VCC divided by RC plus RE. So this point is, say, it is equal to VCC divided by RC plus RE. Okay. Now we can connect these 2 points. So this is what? This is DC load line. This is DC load line. Okay. So, and the output characteristics, it will look like this. Suppose this is IB1, this is IB2, this is IB3, and this is IB4, and this is IB5. Okay. So output characteristics, it is for common emitter configuration. Okay. So this is the DC load line for voltage divider bias circuit. Okay, and this is the output characteristics in common emitter mode BJT. Okay. So from this we can get the Q point. Suppose this is the desired value of IB. IB3 is the desired value of IB. So we can get the value of VCEQ and this is ICQ. That is the operating point at this is the operating point or quiescent point, okay, at no signal. Okay, so this is VCEQ and ICQ. So in this way we can draw we can determine the operating point graphically. Then we will study about the stability factor. Stability factor for this voltage divider bias circuit. How we can determine the stability factor? Okay, so stability factor as it is equal to del IC divided by del ICBO when beta and VBE or IB it is constant. Okay, so it is equal to 1 plus beta divided by 1 minus beta into del IB by del IC. This expression we have seen earlier also. Okay, so for this circuit, how we can determine the stability factor? So the circuit, for this circuit, this is say VCC, this is R1, this is R2, this is RC and this is RE. Okay, now we have to apply Thevenin's theorem to determine IB. Okay, so if we are representing this circuit by using Thevenin's theorem, so it will be looking like this. This is VCC and this is RC, this is RE and it is connected to ground, and this is VTH and this is RTH and the current IB. This is the current IB. So we have what we have to determine? We have to determine change in IB with respect to change in IC, so that we can calculate the stability factor. Okay, so we can write like this: VTH it is equal to, in this input loop, okay, so and applying Kirchhoff's voltage law, it will be IB RTH plus VBE plus IE into RE. Okay, this is current is IE and this is IB. Okay, like this. The current is IB here, this current is IE. Okay, so it is equal to IB RTH plus VBE plus IE. What we can write? IE it is equal to IB plus IC multiplied with RE. Okay, so it is equal to IB RTH plus RE plus ICRE plus VBE. So we can also write like this: VTH minus VBE, it is equal to IB multiplied with RTH plus RE plus IC multiplied with RE. Okay, so this is clear. then how to determine? So we have written Vth, it is equal to Vth minus Vbe, it is equal to Ib multiplied with Rth plus Re plus Ic into Re. Okay. Now suppose this is equation A. Okay. Now what we have to do? We have to apply del by del Ic. We have to take the differentiation of this with respect to change in current Ic. Okay. So it will be 0 minus 0 because these two quantities are independent of Ic. Okay. It is equal to del Ib by del Ic into Rth plus Re plus Re. We can write like this. So from this we can write del Ib divided by del Ic, it is equal to minus Re divided by Rth plus Re. Okay. So it is del Ib by del Ic, it is equal to minus Re divided by Rth plus Re. So how to determine the stability factor? As it is equal to 1 plus beta divided by 1 minus beta multiplied with minus Re divided by Rth plus Re. Okay. So the stability factor, as it is equal to 1 plus beta divided by 1 plus beta into Re divided by Rth plus Re. Okay. So this can be written like this: 1 plus beta into 1 plus Rth by Re divided by 1 plus beta plus Rth by Re. Okay, stability factor. So this is the expression of stability factor in case of voltage divider Vce circuit. Okay. So from this expression, what we are saying? Suppose the ratio Rth by Re, if this ratio is very small, okay, then we can neglect this. If we are neglecting these two quantities, that is the ratio of Rth by Re, if it is very small, then it can be neglected, these two terms. So in that case S will be equal to 1 when ratio Rth by Re is very small. Then S it is equal to 1 plus beta when Rth by Re is very high. If Rth by Re it is very high. Okay. So the value of stability factor. So the value of stability factor for this voltage divider Vce circuit, it varies from 1 when Rth by Re is very small to 1 plus beta when Rth by Re is very high. Okay. And in practical case, stability factor for this circuit, it is approximately in the range of 10. Okay. Now we will see an example based on based on voltage divider by circuit. This is voltage divider by circuit. So in this circuit, all the parameters R1, R2, RC and RE are given. VCC is given as 22 volt. Beta, for one case it is 100 and for another case it is 50. It is given. Okay, and this is made up of silicon BZT. This is made up of silicon transistor. Okay, so what we have to see, we have to determine the operating point. So operating point means we have to determine IC and we have to determine VCE when beta is equal to 100 and in another case when beta is equal to 50. So we will see the effect of change on beta. We will see the effect of change of this beta on the operating point. Operating point means IC and VCE. So if beta changes, then what will be the effect on the operating point for voltage divider by circuit? We will see in this example. Okay. Now we have to determine IC and VCE. So how we can determine it? Okay. So in order to determine IC, first of all we have to determine IB. Okay. IB. Okay. So we have seen for a voltage divider bias circuit, we can determine IB. It is like this. IB it is equal to VTH minus VBE divided by plus 1 plus beta multiplied with RE. Okay, so this equation we have seen how to determine IB. Okay, so we can determine VTH. How we can determine VTH? VTH it is equal to, so VTH we have to determine across this R2. Across this R2 we have to determine VTH. So VTH it is equal to 3.9 kilo ohm divided by 39 kilo ohm plus, this is 39 kilo ohm plus 3.9 kilo ohm multiplied with 22 volt. Okay, so in this way we can determine VTH. Okay, if we will calculate it, it will be equal to 2 volt VTH. Okay, so VTH is 2 volt and VBE means this is base terminal and this is emitter terminal. In active mode, when this base and emitter junction it is in forward bias, condition, then VBE it is equal to 0.7 volt divided by RTH. How we can determine RTH? RTH is the Thevenin's resistance that we are seeing across this resistor R2. So it is RTH, it is equal to this resistor in parallel with this resistor. So it is equal to 3.9 kilo ohm in parallel with 39 kilo ohm. 3.55 kilo ohm. So it is equal to 3.55 kilo ohm plus 1 plus beta. 1 plus beta means it is 1 plus 100 into RE. RE is 1.5 kilo ohm. Okay, it is like this. So we can determine VTH. VTH it is equal to 2 volt. So in this way we can determine the value of IB. In this way we can determine the value of IB. This is IB. Okay, so IB it is equal to VTH. So VTH it is equal to 2 volt, VB is 0.7 volt, RTH is equal to R1 in parallel with R2. It is 3.55 kilo ohm. 1 plus beta, 1 beta is 100, RE is 1.5 kilo ohm. This is R1, this is R2, and this is RC, and this is RE. Okay, so first of all we have to determine IB by using this equation. Okay, by using this equation we have to determine IB. Okay, how we can determine VTH? VTH is the voltage across this resistor R2. Okay, so we have just now calculated VTH, it is equal to 2 volt. Okay, so VTH it is equal to R2 divided by R1 plus R2 into VCC. Okay, so in this way we can get the value of VTH. VBE it is 0.7 volt because this is made up of silicon, and this base emitter it is in forward bias condition. Okay, and RTH, how we can determine RTH? It is equal to R1 in parallel with R2. So 39 kilo ohm in parallel with 3.9 kilo ohm, it is 3.55 kilo ohm. And 1 plus beta is 100 and RE is 1.5 kilo ohm. Okay, so in this way we can determine the value of IB 8.38. It is equal to 8.38 microampere. Okay, so we have determined the value of IB. So we can determine IC, it is equal to beta times IB. Okay, what is beta? Beta is 100. What is IB? It is 8.38 microampere. So 0.84, approximately 0.84 milliampere. Okay, then how to determine VCE? So in the output loop it will be, we can write VCC it is equal to IC RC plus VCE plus IE multiplied with RE. So we can also write like this, plus IC into RE, because IC and IE both are same. So it is equal to IC RC plus RE plus VCE. Okay, so from this we can get VCE it is equal to VCC minus IC multiplied with RC plus RE. Okay, so we can determine the value of VCE. How we can determine? From this expression. So VCE it is equal to VCC means 22 volt minus, what is the value of IC? 0.84 milliampere into RC. RC is 10 kilo ohm plus RE is 1.5 kilo ohm. Okay, so it is equal to 12.34 volt. Okay, so if beta is equal to 100, the value of IC it is equal to 0.84 milliampere, and VCE it is equal to 12.34 volt. This is when beta is equal to 100. Okay, now we will see VCE and ICE when beta is equal to 50, means when beta is reduced to half. Earlier it was 100, if it is reduced to half, means if it is reduced to half means if it is reduced to 50, then what will be its effect on the operating point? We will see. Okay, so again for this beta 50, we have to determine IC and VCE. So again we have to determine first IB. It is equal to VTH minus VBE divided by RTH plus 1 plus beta multiplied with RT. Okay, so IB, it is equal to, for 50 it is equal to VTH minus VBE divided by RTH plus 1 plus beta RE. So first of all we have to determine VTH. So VTH, it is equal to voltage across this resistor R2, okay, so it is equal to VCC into R2 divided by R1 plus R2. VCC is 22 volt, R2 is 3.9 kilo ohm, and R1 plus R2. R1 is 39 kilo ohm, R2 is 3.9 kilo ohm. Okay, so it is the same, 2 volt, and VBE is again 0.7 volt. What is RTH? RTH is equal to, so it is equal to 2 volt minus 0.7 volt divided by RTH. How we can determine RTH? RTH, it is equal to R1 in parallel with R2. So the same value equal to 3.55 kilo ohm. So it is equal to 3.55 kilo ohm plus, only change is here, it is beta. So 1 plus 50 multiplied with RE, it is 1.5 kilo ohm. 16.24, it is equal to 16.24 microampere. Okay, it is equal to 16.24 microampere if we will calculate this. Okay, so if we are getting the value of IB, how we can determine IC? So IC, it is equal to beta times IB. Okay, so here beta is 50 multiplied with IB, it is 16.24 microampere. Okay, so the value of IC, it is equal to 0.81 milliampere. Okay, and again we have to determine VCE. VCE, it is equal to VCC minus IC RC plus RE. Okay, so VCC is given 22 volt, IC it is 0.81 milliampere, RC is 10 kilo ohm, RE is 1.5 kilo ohm. So 12.6, it is 12.69 volt. Okay, if we will put all the values, then we will be getting VCE as 12.69 volt. So what we can write, IC, it is equal to 0.81 milliampere, and VCE, it is equal to 12.69 volt. Okay, when beta is equal to, here beta it is equal to 50. Okay, so what we are saying? When beta is equal to 100, the value of IC is 0.84 milliampere and the value of VCE is 12.34 volt. Okay, now if beta is reduced to 1/2, means 1 by 2 into 100, if beta is reduced to its half, then again IC and VCE, its change is very less. Okay, so here IC, it is 0.84 to 0.81 milliampere. VCE, it has changed from 12.34 to 12.69 volt. So we can conclude that in voltage divider bias, for voltage divider bias circuit, the operating point means Ic and Vce are almost independent of beta. It is almost independent of beta. Here we have reduced the beta to 1/2. Then we are seeing very slight change in the operating point. Okay, so we can conclude that for a voltage divider bias circuit, the operating point is almost independent of beta.